is, I can send it to you.
Yeah, thanks. Test, test, awesome. Okay. Before I get started, my watch says that my heart's beating at 140 and I can't feel my hands. All right, we're good? All right, hi everyone, I'm Winston. I'm gonna talk to you guys about studying young star clusters using color magnitude diagrams. No introduction, because this is like 2 years of work in 8 minutes, so let's just get started. So over here we have a color magnitude diagram. It's a scatter plot of stars with their color on the x-axis and their apparent brightness in magnitudes on the y-axis, color magnitude. So we have the main sequence, red giant branch, white dwarfs down here. And then if you've ever taken an intro astronomy class, there's an HR diagram, same exact features. They convey the same information. Awesome. So just a quick little review on star formation. We have a big cloud of gas that's going to have minor fluctuations in density, and as it collapses under its own gravity, those tiny little dense clumps are going to become more dense, and then we have a feedback loop that leads to the formation of the star. So we're going to start with the forward modeling process, where we start from theory and try to figure out what a CMD might look like. So first we want to simulate the formation of the cluster. This is done in a previous study, actually, and they found that the main parameters that we care about in terms of the rate of star formation are going to be the density of the gas clad, because it's going to have more material to work with, and then the speed at which that material comes together. For us, we're mainly interested in the outputs of the simulation because it gives us a big table of stars with their ages and masses. So then we move on to what age and mass tell us about a star's appearance. As Professor Vaughman likes to say, I don't know if she's here, if all you have is a hammer, everything looks like a nail, so that's the hammer. That is the hammer. It is an isochrone, which is a curve in color magnitude space that sort of tells us how the star looks, varying its mass, but holding everything else constant. That's our sun right there, and then that's like what a brown dwarf would be. So once we have the age and mass from the simulation and our expectation of appearance based on age and mass, we can make the color magnitude diagram. Because there's like tens of thousands of stars in these simulations, actually I don't know about tens, but it's really inefficient to make one of these curves for each star, just because one of those curves takes a minute to make. So for thousands of stars, you'll be sitting there for a day. So instead, we just make a grid that's close enough so that we can interpolate between them, and then we just plot them all there. Everything looks good. So now we want to think about how those cluster parameters affect how that diagram looks. As I said, we have density, we have the speed at which it collapses. Intuitively, as I said, more dense, faster star formation, faster collapse, faster star formation. So right here we have a plot of age spread varying with time, and then we see our highest age spread simulation is the one that collapses the slowest. So if those two parameters affect how the rate of star formation does its thing, and the rate of star formation affects the age spread, we look at this isochrone grid, and we see if there's a spread in ages, there's going to be a spread on the y-axis. So transitively, those cluster parameters are going to show up in our diagram. So let's plot 6 different simulations of different collapse speeds, and we see that we have there's a spread in spreads. I don't know. It's pretty tight right here. It basically follows the curve exactly, and then once we slow down the collapse, it opens up a little bit, opens up a little bit. That's quite open. And then you guys might think that that one's less open, but that's just because the cluster hasn't had enough time to form all of its stars yet. So why was there that latency? Okay, so we have CMDs that we can make from theory. Theory only gets you so far. So now we want to take a look at observational data and see if that agrees with our models. So we're going to take a star from a JWST data set and try to plot that with our isochrone. Oh, it's not even close. Okay, so the reason why that happened is because there's a lot of gas and dust between us and a star, and dust has the propensity to absorb higher energy photons, so that causes it to look more red, because those are lower energy photons, so we call that reddening. You can also call it extinction. I'll use those interchangeably. So ideally, if reddening moves the isochrone down and to the right and the point is down and to the right, we'll just add some reddening. Okay, great. So now it looks like our star is 1 million years old with, I don't know if you guys can read that, 0.405 magnitudes of correction. Problem solved. No, not really. So we don't really know if it's 1 million years. It could be 2 million years old and have slightly less reddening. And just by looking at a star, you can't really tell. And then even if we did know exactly how much gas and dust are between us and a star, let's say we had a point right here and D reddened it to right there. Is it half a million year old or 20? Again, we don't really know. So we're kind of in a Mexican standoff here. We have three free parameters and they all change based on the others. We can try to break that degeneracy by assuming one age. A lot of clusters are pretty young without age spread, so that's a reasonable assumption. So then we can try to guess the properties of the star, but there's still going to be this push-pull dynamic between the mass and its extinction. So the best we can do, so let's go ahead and do that. We're going to use a chi-squared test and this horribly drawn reddening vector. Basically, our isochrone is going to like take tiny little steps towards this point, and we're going to draw a line from every point in this curve to that point, like an Archimedes death ray. And we're going to take a look at the length of this line, and if it's short enough, we can say like within the uncertainties of the measurements, yeah, it might be a good fit. So, oh my God, what is happening? So after we do that, we get this. We have this big band of masses and extinctions that could be a good fit, where that green X is our best fit. That yellow star is an estimation from another study. So it's pretty, I'd say that's kind of consistent. And then we do that for a bunch of stars, and we find that our fits are pretty tight where we compare my values on the y-axis and the other paper's values on the x-axis. There's a bit of an overestimation going on there, but it's still passing the chi-squared test. So there's a chance that he underestimated. This is still a work in progress. We could improve this by adding more filters. You can think about it two ways. If you're a statistician, you're adding more dimensions to your regression model, so you're going to get a stronger prediction. If you want to think about it like a physicist, each of those filters is a little slice out of this black body spectrum. So the more points you add, the more dots you can connect. Literally just last week, I added one Hubble Space Telescope filter, and we can see these overestimations are being brought closer to that identity line. There's a chance that that whole chi-squared thing might have been just like a year-long rabbit hole that I just did. Since we want to study the entire population, there's a chance that we could just put our trust in the law of large numbers and just move the entire population on top of the grid, and it might be good enough to compare spreads. So now we're at the end. I just threw like a bunch of slides at you guys, but we've seen that our models are pretty good. They respond to how they respond to cluster parameters like we expect. The reverse process needs a little bit more work because of that Mexican standoff, three-way degeneracy, and we would need more data to break it, such as like looking at how stars interact gravitationally to figure out their mass, et cetera. So until we do that, this is really only like a good diagnostic tool for very young clusters and still kind of imprecise at that. So thank you everyone for listening. I'm going to open up to questions now. Are you gonna?
We've got time for a couple questions.
Are you picking them or not?
You can pick.
Okay.
Is there any hypothesis you have for why the model was so much more accurate with lower masses compared to the higher masses?
So I think it's partially due to the shape of the isochrones. If you go back here, you can see that like it's the reddening vector kind of goes this way. So if you're up here, like if you don't know how much reddening you have, you can just kind of keep going and you'll intersect something at any given point. Same down here. So then we have this like middle spot where it's okay. You can change the filters to sort of change up the shape, but you're still going to run into similar problems. Yep.
Is there any data to suggest what rendering value you would have to do to fit to the isochrome, or is it just like you want to fit to the isochrome, that's the rendering value you need to pick?
So again, like we don't know exactly like how much gas and dust is between us and a given star, and it changes from star to star. You can get a decent like average value for it, but I would say you probably don't want to pick a reddening value that fits it to an isochrone, especially because once you have this grid, you really don't know which one you want to get it to lay on top of.
All right, let's think.
Oh, there's one more.
Yeah, okay, let's do one more.
Yeah, you.
All right, so have you considered like what is the dimension of the grid you're trying to?
I can't hear you.
Is there a mic? What is the dimension of the grid you're?
Oh, yeah, I didn't really go over it. So this is all based on the Pogson magnitude system. It's like a reverse logarithmic system where a lower number means it's brighter, and then over here it's a difference in filters where you take a bluer filter and a red filter and you subtract them. So then blue things are on the left and red things are on the right.
Okay, let's thank our speaker one more time.
I
I don't think we have enough time, sorry. Oh, perfect. I didn't realize he had brought his own laser pointer, and I spent about like 2 minutes trying to like convince myself, oh, it was always that bright.